folks at home. William and Katie were talking about, yes, the correlations and how Anier is dominating this right now with a high score of 207 or 217. So, yes, as you're watching this, so this is something you need to be thinking about or not, right? Completely up to you. If you're not into accolades and prizes and things like that, but it's a tough score to beat. Anier has been working at this for a while, so. Again, currently undisputed queen of guess the correlation. So something to think about. And this isn't working. We transition. Talk about use the stage hand here. There we go. Okay. Questions about anything that we finished up with last time. Okay. So we went through some examples of just our one-way repeated measures Anova models, and we had a couple of different sets. One was an ordered means, one was an unordered means. Jack, tell me what you remember about the difference between what are we talking about if we're talking about ordered means versus unordered means.
Ordered is where like the timeline one, so it's like timeline intake at 1 is important for intake at 4 and how they the pattern, whereas unordered is like just random, can be at any pattern, any this before this, or whereas ordered it needs to be 1 to 4, let's say.
Yeah. For our ordered data sets, this is a methods piece, right? We need to be thinking about the sort of sequence of repeated measures. Does this have inherent meaning to it that starts to become important, or can we just kind of like place these things wherever we want to, right? In this first one, we're looking at sort of changes in pattern of means over successive assessments in an inpatient setting. We've got symptoms measured in intake, 2 weeks, 3 weeks, 4 weeks. There's a natural progression there. Like I mean, you could honestly for the omnibus test, that F, you could put these in however you wanted to. It's not going to change your omnibus test, but it's not going to make any sense in terms of like how you're going through and setting this up. Versus here, we're talking about vignettes that we've gone through and counterbalanced. So it doesn't really matter which one of these vignettes you load up first into your model. Because there's no natural order to this, okay? Starts to become really, really important in thinking about this and thinking about like, how do we go through and start to do some meaningful follow-ups with this, okay? So remember that what we did here is we went through and talked about going through and running these omnibus tests. So we walked through so the outputs for these. And for both of these, we found evidence that against the null model of no difference in means across repeated assessments, okay? That is your null model, okay? That mean at time 1 is equal to the mean at time 2 is equal to mean at time 3. There's no shift in this, okay? Remember that our repeated measures ANOVAs they're not measuring trajectories. They're not measuring change even. They're just looking at whether or not the pattern of means are equal. Now we'll go through and infer things about trajectory and change and things along those lines. But if you're wanting to look at a specific model of trajectory, change over time, things along those lines, this is not your model. That's an HLM, that's a growth curve model, things along those lines where you're going to get a function that describes change over time. We're not getting a function that describes change over time here. This is just straight up or my means different. Now we infer things about change in terms of like whatever our output is, but want to just be careful when you're interpreting this, right? Again, the null model here is that going to be mean at time 1 is equal to mean at time 2 equals blah 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 to mean at time so whatever you've got there. Okay. All we're doing is looking at changes in means. Okay. People understand this starts to become an important thing when you're thinking about what these models do and more importantly, what they don't do. But for both of these, what we found was that we have evidence for differences in means across repeated assessments. Okay, here when we go through and take a look, and this is just what our p-value RF is saying, is that yes, this is testing against the null model of equal means across repeated assessments. Here, very clear. Is p equals 1.42 times 10 to the negative 142nd, right? That's basically, this is saying if the null model is true, these data cannot occur. Functional, right? And with this one, if we just take a look at it, we're saying reduction over time, right? And you're saying like, okay, very clear that what's going on here. This was a little bit different here. Again, the same conclusion. I'm wording it a little bit different. We have fairly clear evidence against this null model, even though the mean values here were very different, right? These were all actually pretty close to one another, all sort of ratings of 7, but still with the sample size, we have incredible power to test sort of whether or not within a individuals, whether or not we're seeing shifts. Okay. But here, the interpretation not so clear as exactly what's going on. We're just saying that yes, the pattern of means seem to change across repeated assessments at least one point. We just don't exactly know where that's happening, right? So we have to think a little bit more carefully about where we're going to go through and jump in and start to look at this. Okay. Talked about some different effect sizes. Catherine, can you tell me what sort of the draw of generalized zeta squared was when we're thinking about effect sizes?
Like more accurate, like you would consider as like the between treatment error or effect that like was pulled out of the other calculations.
Yep. Remember that. So when we're going through and we're partitioning out variability in these repeated measures models, what we're doing is all the between stuff, all the different individual difference variability that gets pulled out right at the start, right? And so what you'll see is a partial eta squared. Well, in the one-way model, it's just an eta squared for each one for our main effect of whatever our measurement is. It's just that's going to look a lot bigger than it would if we were to do a between, because that's got all of that individual difference variability pulled out of the denominator. Generalized zeta squared, we're just kind of punching this back in so that we can go through and have something that would be comparable to what we might see with a between groups. Okay, so again, for this first problem, our partial eta squared, which again is just an eta squared in the one-way case, it was like 0.5 something, right? 0.53 or things along those lines, saying that the repeated assessment was accounting for about point. Oh no, is it even bigger than that? Oh no, it's not. 0.525, right? So for the eta squared with this is saying that repeated assessment is accounting for over 50% of the total variability in your model, right? But that total variability is just the stuff that the individual different stuff has been pulled out, right? So it's not actually total variability in the model. It's the repeated assessment is counting for about 53% of the within groups variability within the data set. Okay. Here, generalized A squared, we take that individual difference variance and jump that back in. Now we've got 0.263, basically cut it in half, right? More than in half. And now what we can say here with the generalized eta squared, we can literally interpret this just as we would our normal eta squared and just say that our repeated assessment is accounting for 26.3% of the total variability in this model. So we've just plugged everything back in here, right? Same thing here for support. This was 0.09 something, right? And we go through and we take a look at our vignettes. We're down to 3.8% of the total variability. So much difference in terms of the magnitude of these. And the idea with generalized eta squared is this, just that we are accounting, sort of trying to give this a metric that makes more sense in terms of the types of effect sizes that we're usually used to seeing. All right, and then there was a cat picture, and then guess the correlation, and now we're all back up to speed. Okay, so what we need now to go through in our one-way model is think about, I guess before we sort of jump in, any questions about kind of the logic what we're trying to accomplish with these designs or with this specific analysis. Okay. So what we want to do now we've got an omnibus test. An omnibus test says the null model is implausible given the data, right? So what we want to do now is we want to say, okay, where are we seeing differences in these means? Like what's going on, what's happening, okay? Now, again, just like when we were running our regular ANOVA, what we need to do is think carefully about how we're going to go through and start to tease apart specific effects, okay? The problem with our repeated measures is designs, once we start to get into a full mixed factors, repeated measures analysis, is one, we've got additional assumptions, and then we have possibility of both within and between factors, and then also some crossed factors. It gets pretty complicated, okay? So we need to be thinking carefully about this. The way we're going to approach this isn't any different than what we did last semester, okay? The tools are going to be the same. We're just going to tweak them a little bit and need to think a little bit more carefully about how we're applying these, okay? So again, common procedures for looking at specific effects. We're going to talk about trend analysis. This is a little bit different in terms of what we've seen, but this trend analysis is just a linear contrast. Okay, we had set up previously last semester linear contrast to go through and tease apart sort of this group of means versus this group of means. Here we're just setting it up to start to look at specific trends or patterns. Okay, and we'll talk about what that looks like. We can also set up just linear contrasts, planned contrasts, planned comparisons, like just the mean-based test that we had done last year, last semester, and then sort of also always available to us as exploratory post hoc testing. Exploratory post hoc testing should be only used in rare situations. It's just going to be so much stuff, like you need to have a plan for what you're going to do with these. Hopefully you have some specific hypotheses about how things are going to turn out. Is if you fall back on this, it's going to be a mess and you're going to lose a ton of power. You don't want to be in this land with this, okay? Want to have an idea for what you're looking for with these types of analysis, okay? Now, how do we go through and determine what approach we're going to take? First thing, specific hypotheses. Why did I set this up in the first place? Okay. Charlotte, with your thesis, right? We're talking about, and I would like to use something like this, right? Our question will be, what are we expecting to see? How do we expect things to play out? And that's going to drive the types of contrasts or things like that that you might set up to tease out individual effects, okay? We want to think about conceptual considerations. What have I done methodologically? How have I set this study up? Like what's going to make sense? And what are things that don't need a statistical test? What are things that like I can just assume are the way they are, sort of uncontroversially? Want to think about your study design, and then the number of type of effects observed, right? Again, always wanting to think about like managing and sort of balancing out sort of our power versus corrections for repeated comparisons. This is where in applied, if we're doing good science, things start to get tricky, right? We know that in psychological science, we're almost always underpowered all the time, right? And certainly if the null model is never correct, we can't make type 1 errors. We can only make type 2 errors. And we're going to do, I guess we can make type 1 errors if we guess in the wrong direction, right? But literally, the answer will never be 0 to 1 million decimal points. So it's just like, are we getting the right direction, right? So in that perspective, controlling for type 1 error doesn't make any sense because I can't make a type 1 error. But functionally, if I just go through it and I continue to punish my data with 15,000 pairwise comparisons, eventually something will come up, right? And we got to sort of try and balance this out, okay? So this needs to be thoughtful, planful in how you're going to go through and approach this, okay? So go back through, sort of jumping back into last semester. We're talking like last November. Seems like a long time ago. It's actually not that long ago. But at the end of your first year of doctoral studies, it might seem like a long time ago. Think about how do we go through and approach this. thinking about error, first thing we need to remember to sort of consider is our per comparison error rate. Okay, per comparison error rate is this is just your alpha. Okay, this is just whatever you set for any individual test. So Finn, what is your alpha level for any individual test? Almost certainly
0.05.
105, right? This is just industry standard. Like you can go through and crank that up and make that more stringent if you like, and there are situations where that might happen. But in general, you can set alpha to anything you want. It's just within the context of our science. If it's less than that, if it's 0.1, you're probably not going to get much traction unless you have a really, really, really good argument for why that's necessary. They rarely come up in the types of work that we do, but it's probably going to be 0.5 almost all the time. Okay. We need to compare this or sort of consider this with respect to our family-wise error. Okay. Family-wise error, remember, is our probability of committing at least one type 1 error across a series of comparisons. Okay. So our family-wise error specifically is given as 1 minus alpha to the C power, where C is the number of comparisons that we're planning to do. Okay. So again, if we were to make 4 pairwise comparisons in a set, our family-wise error across those 4 comparisons, if each one are conducted at alpha 0.05, my family-wise error rate is 0.185. Cindy, if you said, hey, Josh, I'm going to run my thesis and I'm going to set my alpha to 0.185, what would I probably tell you? Probably not, right? That's not an acceptable rate of error for type 1. It's way too lenient, right? But the idea is my family-wise error, the likelihood of me, the probability making at least one type 1 error across those 4 comparisons at alpha 0.05 is close to 20%, right? That's not going to be something that most people are going to identify as sort of acceptable, okay? So we want to be thinking about that. Now, one thing we want to do is thinking about sort of this is different than regression. Sometimes we get sort of turned around at that. I've got 5 predictors, and so I'm just going to Bonferroni correct these for each individual predictor. That's not how we run things. That's not how we do things. I get the logic behind that, but this is one model. We're running everything simultaneously. Like we're not running individual corrections for individual predictors, right? But when we're doing follow-up tests, this is something we need to be thinking about, okay? We know that our family-wise error is going to be bounded by alpha and C times A, right? C times A, what is this? We're taking the number of comparisons times alpha. What is that, Charlotte? What's one of our favorite corrections, or at least in psychology? What's one of our favorite corrections to apply to things? Starts with a B. Bonferroni, there you go. Sounds very Italian. Sounds like a fancy car. Watching F1 stuff back. I drive for Team Bonferroni, right? This is your Bonferroni correction, right? It's just like the number of comparisons times alpha, right? Your family-wise error rate is going to be less stringent than that. It's going to be somewhere in between alpha. It's probably going to be close to this, but this is where we start to get into some differences between Bonferroni correction and like a Dunn-Siddick correction. Dunn-Siddick corrections should have taken this into account as Bonferroni, right? But just in terms of thinking about where our error rates occur. Do we Bonferroni as a post hoc test? Is Bonferroni a post hoc? Should Bonferroni be used as a post hoc correction? No, and if you didn't sort of get it from context and inflection, the answer, no, it's not. Bonferroni should be used to go through and control for a small section of pairwise. Now, you'll find it in SPSS under post hoc stuff. Don't do that. It's way too stringent. Like you're going to hamstring yourself, right? But again, thinking about sort of some of our strategies here. Okay, so this is what we're trying to navigate, manage is our increasing error rate as we work through our comparisons. Okay, so again, this is all recap. This is stuff from last semester, but strong recommendations. We don't do this enough. Be selective, right? Only look at things that are meaningful, particularly when we start to get into these repeated measures and mixed designs. There are lots of things that you could test, that either one, don't make sense, or that you can just look at, you don't need a statistical test for. Let's not waste power on that, right? Let's be reasonable and ask reasonable questions, right? But this is going to require you taking a step back and thinking about, okay, what am I doing? What are the comparisons that are going to be meaningful? And so what's going to give me the answers or tell the story that I'm trying to tell, okay? Again, testing all possible comparisons. If all possible comparisons are not meaningful and interesting, it's a poor approach. Because if you're being responsible and you're charging yourself for each one of those, you're just spending cash and running out of money and sort of making things harder and harder and harder for yourself to get answers to a bunch of questions that no one asked in the first place and are as interested in, right? So we gotta sort of watch out for this. And this is the biggest thing. It just complicates a straightforward impression, right? Like, or straightforward interpretation. We'll see this when we're looking at our ordered means. There are lots of questions that we can ask and lots of comparisons that we could make that I don't know why we would. Like, you certainly physically can't do them, right? And the statistics police isn't going to show up on your door and put you in cuffs if you were to do it. It just like, why would I create problems for myself, right? I'm assuming as a reviewer that anything you test it for a reason because you thought it was important. And so if it comes up as something that's interpretable or not, I need you to tell me why that is, right? And if you didn't care, and you just tested it because I was just being lazy and I tested all sorts of things, sometimes those are going to come up and then you're going to have to explain them. Yeah, I don't got an explanation for that because I don't know why those two things would be different, right? That's adding bulk and nonsense to your discussion section. So you're wanting to go through and tell the story that's consistent with your hypothesis, this with your theory. So you want to be thinking about this, okay? So the goal is to choose a strategy for approaching these that's going to manage your family-wise error across planned and unplanned comparisons. SPSS is not going to do this for you. Stata is not going to do this for you. You need to have a system and a plan for how do I go through and approach this. Okay. And there's not one answer, right? It's not like, oh, here is the solution. There are going to be an infinite number of ways you can go through and approach this. Some of them are going to make more sense than others. Some are going to be more defensible than others. It's up to you to say, here is my plan. Here's what I'm going to do. This is why it makes sense. And then we can have a debate about whether or not we could have done something different, which you generally will with reviewers. But so long as you have a reason for doing things in the first place, it puts you in a much better position than, I don't know, I just did it because we had a problem set and that's the way we did it, or this is the way you have to do this. None of that is true or a good way to go through and approach this. Okay. So again, just quotes from Hal, which is fantastic, and just think about like anything you do in your study, just have a reason for doing it, right? I should be able to say like, why did you do it this way? And you should be able to say, this is logic behind this. Okay. All right. Going through talking about the difference between our a priori and our post hoc tests. A priori comparisons, generally involving a small set of theoretically meaningful comparisons, and we choose these before we collect the data, okay? Anything that you do after you look at the means is post hoc, okay? This is stuff that you plan, this is calling your shot, okay? Playing a game of horse, you're saying like, I'm shooting from here, this is what I'm going to go through and try and sort of demonstrate with this study, okay? Again, small set of theoretically meaningful comparisons. If you've got 15 a priori hypotheses, that's probably too much. You need to sort of narrow things down, sort of think about like, what is the crux in the stuff that I'm most interested in? What we would typically do is just look at these as linear contrast or independent sample t-tests. And the thing here is that by convention, we typically test these at per comparison error rates, okay? Because this is something that a year and a half ago when I started my thesis, this is what I laid out. These were the hypotheses that I had expected. Cindy and Charlotte, this is what we're working on right now. We're saying like, here's what I'm expecting to happen in these data. I've laid these out. Here is my marker. You go back to the notes and the emails that we did a year and a half ago. This is where we're at, right? This is the stuff that we can go through and lay out at per comparison error rates. The idea is that like, I'm not capitalizing on chance or random things I'm seeing in the data to magically find stuff, okay? Now, if you want to be conservative, if you have a wildly overpowered data set, right? Or if you just want to be like really sure, like the potential to say that you have found something when there isn't something, you just want to be really careful. We can have some correction for family-wise errors, bond frontier and SIDAC. Remember, these are just changes to your p-value. Okay, these do nothing to your actual test. You just it's instead of comparing to alpha equal 0.05, this is just changing your alpha level, right? So you're running the same stuff with bond fronting and density. You're just changing the goalpost around, right? So now we don't get to claim victory at 0.05. We can only claim victory if we're under 0.025 or under point sort of 0.133 or something along those lines. Okay. This is in contrast with our post hoc comparisons. This is typically looking at all analysis of all pairwise comparisons and anything that post hoc is going to happen after we've generated our data and taken a look at these. This, unfortunately, and like I'm not like this isn't like a holier than thou conversation. Like I do plenty of stuff. Like once I go through and see like, oh, that's interesting. So what am I doing there? But recognizing that as soon as we do that based on statistical theory and probability theory, what are my eyes doing immediately as I'm looking at that? I'm like, what's the lowest? What's the highest? I wonder if those two things are different. And when I do that, then I can come up probably with all sorts of interesting reasons why I really should. These two things have been are really the things I'm most interested in. The problem is that that's all hindsight, right? That's after I went through and identified those as the most likely to be different. And then I generate, now if I beforehand generate like, oh, these are the two groups I really want to see are different. I should have said that before, right? If I only did it after we went through, like, oh, I had a eureka moment, fine. This is a post hoc. You get additional tax for that. Then run a replication and look, test it again if you want to have a less stringent test. Okay. The issue is that these post hoc procedures or these post hoc tests, you get these really, really, really easy in SPSS. It'll just belch out a whole bunch of them. The problem is that then that puts you in a position of like scanning through and trying to find the lowest p values and things along those lines. We got to be really, really careful with this. Okay. Questions about sort of this coming back to people sort of the difference between our a priori tests, our post hoc tests, and things. Okay. All right. And this is an absolute, right? Our limited set of planned a priori contrasts is more theoretically and methodologically defensible defense. I'm not saying that if you go through and you publish something or submit something, that reviewers aren't going to be like, well, what about this? And what about this? Is this different than this? Do you go through and look at this? This is, and I've had these conversations with reviewers like, sure, you could do that, certainly. And that may be interesting for a different research question. It wasn't interesting for my research question, and so I didn't do it. But here's mean standard deviations. If you want to test the hell out of whatever you want to, it's all there in the descriptives. Like you can certainly do that. It's not important for me. This is why I wouldn't do that. This is why it's not interesting. It's kind of a distraction. I've gone through and provided anybody who wants to can go through and do it, but I'm just not going to do that because it's not relevant to sort of the question at hand. And I've been really successful with that, right? I'm not trying to like, you don't, if it's something stupid and small, you're like, fine, fair enough, here you go, right? Or I did it, nothing turned out, so I'm not changing anything, right? But really what we're wanting to see is sort of a planned approach where it's not, is everything different than everything, right? It's, here's the thing that's going through and testing the specific question that I have for this set. Okay. So again, if you default to looking at all possible comparisons, you really need to have a good reason for why you're doing that. Okay. Questions about sort of the general approach. Okay. So running our follow-up tests. Okay. If I have these designs where I've got an ordered outcome, Jack, like you were saying, like, okay, we've got baseline week 2, week 4, week 6. We've got some ordered outcome. Sometimes with these types of questions, these types of analyses, the pattern is what I'm most interested in. Okay, so it's not necessarily the difference between any 2 points. It's overall what's the pattern of means that I'm seeing over the course of my repeated assessment. Okay, going back to our example here is whether or not I've got a patient symptoms that are lower at 2 versus 3 weeks in treatment is probably not super relevant or interesting, right? From a clinical standpoint, where everybody's here clinical, right? Like the difference in treatment means I might have sort of tested at baseline 2 weeks, 4 weeks, 6 weeks, 8 weeks, right? 10, 12, right? The difference between weeks 2 and 4 or 6 and 8, I probably don't care about unless there's something important going on in treatment, like at those specific points. Probably what I'm more interested in is overall, sort of what's the pattern? Am I seeing a decreasing trend? Okay. And this is where trend analysis starts to come in. Trend analysis gives us a test of the shape of means across our repeated measures. Okay. And here we're looking at the effects being dependent on both the magnitude of differences and the order of means. Okay. So this is where what I'm doing is I'm setting up the nuts and bolts, and we won't worry about this. The nuts and bolts of your trend analysis. You just run a contrast, right? All the things we were doing previously with contrasts. That's all you're doing here, except instead of setting up those weights to look at a mean difference across like groups or means or sets of means, you're setting up weights to follow a linear increase or decrease, following quadratic change. You can do it just follows polynomial, right? And what you'll see when you go through and get these in SPSS, you can test. It will give you a trend analysis for a polynomial, one less than the number of observations that you have. Okay, so you need 2 to make a line, so you need 3 data points to get a linear trend. 4 points, 4 assessment points, so get you a quadratic. Yeah, 4 will get you a quadratic. 5 will get you a cubic, right? So it's just sort of what it's going to do is it's just going to give you polynomial shapes, right? So you're going to have a test for just that. So I'll get a test for a linear, and I'll get a test for a quadratic, then I'll get a test for a cubic, and then fourth order, sort of so on and so forth as we move up with stuff. Okay. And what SPSS will do is it will give you each one of these. Okay. Now the question is here, and sort of the trap is you could go down through and let's say I've got 6 assessment points. So it's going to give me trends on a 5th order polynomial. And maybe that 5th order polynomial comes up as having a low p-value. Is there a reason for me to expect sort of this thing to start going up and down in sort of ways like that? You'll get p-values popping up for these all over the place. That doesn't mean that there's anything necessarily interesting or useful going on there. Okay. These are red herrings. You got to be really careful unless you are prepared to make an argument for why specifically the pattern of data across repeated assessments is specifically following a 5th order polynomial. If you can do that, good on you. It's just this is probably not going to be sort of what we're seeing with things. Okay. So generally what we see most often is trend analyses involving just a linear or a quadratic effect. Okay. What we're seeing here is if we're seeing things having a linear change or sort of kind of a curvilinear sort of growth or declines of our quadratics. Once we get into cubic change, now all of a sudden we're starting to get, unless you have a very specific reason to expect things to start sort of jumping up and down based on your manipulation, which you may, but you just want to probably sort of be careful with that. Okay. So our trend analysis is just going to go through and say, are we seeing changes in means that are consistent with a linear reduction? Are we seeing change in means or differences in means that are consistent with a quadratic pattern or things along those lines? Okay. Again, this is just looking at sort of patterns of means. This is not establishing a trajectory, right? Now, we might look at this, run a trend analysis and say it looks like we have a linear trajectory. But again, if you really want to test a linear trajectory properly and specify it, you need to be running on an HLM or a growth curve or something like that. Anything we're doing with this is just looking at differences in means. It's not looking at growth or change. Again, trends analysis is computationally identical to our planned contrasts. We do by hand. You can set your weights up if you wanted to, if you're good at that, but we'll probably just let the software run it if that's what you're wanting to do. Also note that our trend analysis is most generally working best in cases where we have relatively equally spaced assessments. Okay, because what SPSS is going to do is it's going to treat this as all being sort of being equally spaced. I imagine there are things that you could do by hand that start to sort of stretch these out if you needed to. But generally, the stuff that you're just getting stock from your package is going to assume that these are reasonably spaced from one another. So just something to keep in mind. This starts to become problematic when I'm reviewing papers looking at HLMs and trend analysis and stuff like that, where you have this is baseline, and this is, let's say, the end of treatment at 10 weeks, and this is 3-month follow-up, and this is 1 year follow-up, right? And people are like, oh, look, there's a linear trend over the course of treatment. I'm like, well, maybe if you stack those all sort of as if they were equal, but that's a misrepresentation of what's actually happening. This is way farther out than this, right? Like you gotta account for that timeline if you're gonna start estimating stuff. Otherwise, you're gonna get results that don't make any sense. Okay, so just something to think about when we're using sort of these types of analyses. Okay, questions about trend analysis and kind of how we're applying these to order means. And again, SPSS will just spit these out if you're interested in it. It's easy. You just go down through and look and say, what's going on? Do I have a cubic? Do I have a quad? Or do I have a linear? Do I have a quadratic? After that, you want to be pretty specific about like why we would expect that, because you might just see a bunch of small p-values that like are difficult, if not impossible, to interpret. Feeling good about this? Or at least on a conceptual level? Okay. All right. We'll get into unordered means. This starts to get a little bit more tricky. Okay. Trend analyses are nice, but not useful in designs if I've got a repeated measure with no meaningful order. Okay. Let's say like I'm going through and looking at emotional reactions to a series of photographs, right? And these are my manipulations that I'm looking at, sort of like disgust or sort of anger, sort of types of things that I've got a sequence of photographs or vignettes or something like that, and then I'm looking at people, having people respond to, unless there is some reason that they need to be presented in this order. I can't run a trend analysis, because if I go through and I reset like the ratings for these or reset the order, I'm going to get a completely different pattern and trend. And if that doesn't make any sense, then my trend analysis doesn't make any sense to go through and take a look at. Okay. Even if you've got a whole bunch of p-values, all those will change if you just reshuffle the order, right? It doesn't mean anything. Okay. Other thing that can happen too is if I've got a repeated measure that has a meaningful order, but my responses don't follow some polynomial function, like a cubic or quadratic, things along those lines, then trend analysis probably isn't going to be useful, right? It's got to follow sort of some known function. And if I have a specific pattern that doesn't, right, the order makes sense, but I'm expecting, so you're thinking about like, depending on, I mean, like, so surely thinking about kids stuff. I'm they do an ABA design, right, where I've got like several observations sort of with no treatment. Let's say it's a med study with kids, and then we give meds sort of here, and then that goes away, and then we're down here, and then up. Trend analysis might make sense. We would expect that to follow sort of this function here, right? But sometimes, right, I may say, Cindy, you're like, okay, we're gonna do this, and then we're gonna do this thing, and then we're gonna do this next thing that'll keep it here, and then it's gonna go up, and then maybe it goes, I don't know, we're kind of all over the place. The pattern makes sense, it is meaningful, I can't just switch these all around, but the patterns that I'm expecting aren't following one of these. Trend analysis is out, then we gotta think about something different. Okay. So in these situations, what we would do is we would follow up with a limited set of within subject comparisons using either planned contrasts if I'm wanting to look at groups of means or independent sample t-tests if I'm just or paired sample t-tests if I'm just sort of comparing pairwise across stuff. So let's think about our planned contrasts. Remember that our contrasts are allowing us to start to make comparisons across means or sets of means. A t-test is a t-test is a contrast, right? What we're doing is we're just taking this t-test idea and expanding it out to include multiple means that we're kind of clustering together, right? It breaks down essentially to a t-test. It's just I'm able to say, is the difference at times 1, 2, and 3 different than what we're saying at 4, 5, and 6 together, and collapsing that into a more efficient type of question. Again, if we're going to go through and set up our contrasts, and again, this is all just stuff from last semester, what we need to do is we need to set up a specific linear combination of means. Generally, it doesn't indicate this with Psy, right? And here we have a weight for mean 1, weight for mean 2, weight for mean 3. We can shorthand this by saying the sum of the weighted means here. And again, this is just identifying a linear combination as a sum of weighted means here. Okay, if I set all of my weights here to equal to be 1, then Psi is just the sum of my means, right? If this is 1, 1, 1, 1, 1, all the way across the board, then I'm just taking mean 1 plus mean 2 plus mean 3 plus mean 4. That's all the Psi is, right? And that's actually not sort of terribly useful, but like we could set that up. Okay. What we had talked about previously is if I go through and I set my weights equal to 1 divided by the number of groups, what I'm going to get is this Psi is going to be the mean across all my groups, right? So if I've got mean 1, mean 2, mean 3, and I set my weights to 1/3, 1/3, 1/3, Psi is just the average of those three with those 3 means. So again, remembering, so what we can do is play around with our means to start to ask specific, or play around with our weights to start to ask specific questions, okay? And when we set this up so that we've got a set of weights where the sum of our weights equals 0, then what we have is a linear contrast. Okay. So again, we got 3 means, mean 1, mean 2, mean 3. And weight for mean 1 is 1, weight for mean 2 is -1, weight for mean 3 is 0. If I go through and I add these up, 1 plus -1 plus 0 equals 0. I've got a linear contrast. Okay. Finn, what am I asking? What is this set of weights asking in this contrast? What am I testing?
The specific differences between the 3 of those, or? Sorry, can you rephrase?
Yeah, what am I testing? You're almost there. What is, if I have weights of 1, -1, and 0, or means 1, 2, and 3, what am I specifically testing there?
Means 1 or 2.
Yep, I'm asking if means 1 or 2 are different, right? Because this is gonna be mean 1 times 1, minus mean 2, because we've got some multiplied by 0, that makes mean 3 go away, and so this is just a test of mean 1 and mean 2 right here, okay? And so again, we're just looking at the difference between these. Okay. You're on a roll, Finn. Let's try this again. What if we have weights of 1/2, 1/2, and -1? What am I testing here? Again, I've got a linear contrast because if I add 1/2 plus 1/2 plus -1, I get 0. So I got a linear contrast. What am I testing here?
You're looking at all variables?
Yep.
Okay.
And what specifically am I testing? What is this contrast getting at?
If 1 and 2 are different.
Yes, is the combination of 1 and 2 different than 3? Okay. And if I'm going through and I have a question where, again, let's say, Charlotte, I've got a sort of a piece of an ABA design and I want to say I've got two baseline assessment points and then one treatment assessment point. What I want to see is, could I go through and assess if my treatment is different than baseline one and baseline two? Sure, I could, right? But that wastes the test. And if I'm going to go through and get charged for stuff, I can just say these two should be identical. So I'm just grouping those together. I'm trying to see, is the combination of type one, type assessment one, assessment two different than assessment three? I can't do that with just a paired sample t-test, but I can set this up nicely and efficiently with a linear contrast. Okay? It's just giving us flexibility. Did you have a question, Jack?
Yeah, I forget. Like why, how do you decide whether it's like -1 or 1?
We'll go with, yeah, sort of jump in right here. Short answer, Jack, is it's completely arbitrary. It doesn't actually matter. But it starts to like, just to keep, and this will start to be with these types of analyses, keeping everything straight in your head about what I'm doing and what things mean starts to become really important just because there's a lot of information to manage. Okay, so what we're gonna do is we're gonna go through it. First, we're gonna identify the set of treatments to be compared. Like which of these assessment points do I want to include in this comparison? Then I'm just gonna assign weights to the reciprocal of the number of treatments in the total set, or in each individual sets. There are different ways to set this up, but this is sort of an effective way and sort of common way. You could take a whole class on this if you wanted to, probably multiple classes. And if this were the 40s, we might. We're not going to do that here, but just wanting you to think about how to go through and utilize this effectively. And then we're going to assign the coefficients in one of the groups to be negative. Okay. So again, we've got 5 means here, 1 to 5. And what I want to do is I want to compare whether or not assessment points 1 and 2 are different than 3, 4, and 5. Okay, because that starts to make sense. This is important for answering my question of interest. So what I'm going to do is I'm just going to set them up. And then I'm going to assign weights as the reciprocal of the number of treatments in a set. Here we've got 2, easy peasy, those are 1/2. Here we got 3. Assign those as 1/3, 1/3, 1/3. Okay. And then what we do is we assign coefficients in one group to be negative. This is where you want to start thinking about who do I expect to be bigger than the other one, right? And then that's going to make sure that that sign makes some sense when you get the value of your contrast. Here, implicitly, Jack, if I've done this sort of in this manner, what set of means am I expecting to be larger than the other? The blue? Yeah, I'm expecting these ones to be bigger than these ones, right? Because if I do this, if the average of these two is larger than the average of these two, the value of my contrast is going to come out to be a positive number, which is saying that, yes, this is consistent with the way I've set this up. Now, if I flip this around and make this -1/2, -1/2, +1/3, +1/3, does that change anything mathematically in my thing? Nope, it just flips the sign. I just got to be aware that even because if I expected these to be larger, now that negative means that these are larger, and then that starts to get in a weird headspace, right? So it's just easier to set up your values so that it sort of kind of tracks with what you would expect. It doesn't ruin anything. It just makes sure that you need to be looking and sort of keep track of what you're actually doing. Okay. But regardless of which one of these we assign as negative, the sum of these still equals 0, so we're still good. We still got a linear contrast. Okay. So again, shorthand for this is going to be 1/2 times the sum of x1 and x2 minus 1/3 multiplied by the sum of x3, 4, and 5. I just shortened this up with some algebra. See how we did that? And it's fine. Do people see kind of what we're doing here? Right? If we longhand this out, this 1/2 times x1, 1/2 times x2, minus 1/3 x3, minus 1/3 x4, minus 1/3 x5. We just kind of condensing this out to save some space. Other thing too to remember, and this starts to become important, if we've got linear coefficients where the absolute values sum to 2, this is what we know as a standard set. Okay. With this approach, this will get us a linear contrast. Charlotte, is this the only way to get a linear contrast? Nope. It's sure not. I could go through and set these weights. I can set the weights to 3, 3, -2, -2, -2. Does that give me a linear contrast? Yeah, it does. There are an infinite number of linear contrast weights that I can apply to this to set up a linear contrast, right? And all of those are gonna get me the exact same p-value if I work this out, right? What we've done here, though, is gone through and set this up so that I end up with a standard set. And this starts to be helpful because what I can do is I can interpret the value of that contrast as the literal difference between the average of those two groups, okay? If I go through and I make this 3, 3, 2, 2, 2, I've rescaled this, right? It's still giving me the test of the difference between those two. It's just the value of my contrast isn't gonna be the units of my actual scale. And so then I just gotta keep that in mind when I'm going through and sort of testing other things. Does anybody remember where this really starts to become an issue? Or where this was an issue with our factorial designs last semester?
All I remember is that we weren't able to interpret anything from it. It didn't have any interpretable like meaning.
Yeah, it's not something that you can go through and interpret. I mean, you can, it's just like not on an appropriate scale. Does SPSS handle sort of decimals on your weighting very well? No, it doesn't, right? And so what happens is it will give you two decimals, right? So I can go 0.33, 0.33, 0.33. If I do that, do I have a linear contrast? Nope, I actually don't. It's off by a little bit, right? It's gonna be close, but science shouldn't be about close. It should be about doing it right and being accurate, right? And so what I can do is I can force SPSS to give me a proper p-value for this, right? I can set this to 3, 3, -2, -2, -2, and then run that contrast, that linear contrast, and the p-value that I get out of that is gonna be precise, right? But the value of my contrast, my confidence bounds, all that stuff, the effect size that I get out of that on my output, I can't actually interpret that. I have to go through and do those by hand, right? But the standard error you're gonna get will be identical, right? So you're getting stuff that you then very quickly go through and do the hand calculations on your own. You just gotta remember that Stata resolves this by, like, if you go to like place some of this like 6 repeating decimals, it just like sort of translates that over. You can go through and do that. SPSS just won't do it. You need to just be careful in recognizing that what you're getting is not a precise value, right? But sort of recognizing the standard set then starts to become important in terms of interpretations. Okay. Also note that if we start to get dramatically different sample sizes across cells, this starts to impact the calculation of linear contrasts. Okay, with our one-way design, do we have to worry about differences across cells? No, because you got the same number of people. There's no between, right? It's just all the same. But as we start to rotate in between factors, what we can start to get is wild differences in your cell sizes. And then that starts to degrade inferences that we can draw from this just because it starts to chip away at stuff. So we talked about last semester calculating linear contrast for our between groups designs, okay? We can use some variations of that same formula here to get within groups contrasts, okay? So here, contrast for our repeat measures ANOVA, and this is what, remember that there are ways, and sort of classic way to go through and calculate contrast are to give you F tests. SPSS doesn't do that, it gives you T tests. T tests are nice because it's T, we understand, know, and love T. This is all that SPSS is doing when it's correct, when it's calculating within group contrast. Value of our contrast is just the sum of our weighted means. And our t-test is going to be the value of psi over the square root of the sum of my squared means, or the sum of my squared weights, multiplied by mean squared error from my repeated measures ANOVA table, divided by n is going to be the number of people in that repeated measure. Okay. And then what we do is we compare this test statistic against the t in degrees of freedom we take from the overall ANOVA table. So remember, if we've gone through, we've done everything correct, there's a couple of benefits that we get from doing this. Okay. One, we get a mean squared error estimate that should be much more stable if we haven't violated our homogeneity variance assumptions, because the assumption is that variability time one is equal to variability time two is equal to variability time three, so on and so forth, right? So our mean squared error, if that holds true, is based on the calculation of a whole bunch of observations as opposed to just maybe a couple time points. So we should get a more stable estimate right here, okay? Other thing that we're getting here is we're comparing this with a degree of freedom, with a critical T taken for the degree of freedom from my overall ANOVA table, okay? Is my overall ANOVA table degrees of freedom based on degrees of freedom for just 2 time points? Nope, it's based on the whole design, right? So because of that, Catherine, if I were to run through this as using this contrast versus just like a independent or a sort of paired sample t-test at time 1 and time 2, is my degrees of freedom going to be higher for that paired sample t-test or degrees of freedom that I pull from the overall ANOVA table?
Higher for the t-test?
What's that?
Higher for the t-test?
My degrees of freedom.
Oh. Higher from the Andover table?
Yeah, no table, because that's got a whole bunch of observations there, right? So cross repeated assessments. As my degrees of freedom go up, what happens to my critical value?
Yeah.
It goes down, right? So what I'm doing here is I'm testing against a less stringent test than if I were to go through and test against sort of my standard pair sample test, okay? So we're gaining power with this, assuming this is a valid estimate of my sort of within groups stuff. But for pairwise comparisons, if I'm just interested in a couple of different time points, completely fine to just fall back on paired sample T's, okay? What I do is I give up some power, right? Because I'm not capitalizing on a sort of a more liberal critical value with this. But what I do with this is I dodge some of the assumptions of sort of what's going on with this, right? Because we can see in certain types of things that maybe variability at baseline where everybody's coming in and everybody's super distressed, everybody's kind of at the same point if we're thinking about treatment setting. By the time we get to the end of treatment, we could have wide variability in terms of where people are at, right? So we've got a violation of homogeneity of variance within groups, right? Which now all of a sudden starts to make this be suspicious as a good like overall representation of whatever 2 points I'm trying to look at. And so then that kind of puts in and calls into question validity here. It just gets complicated. I don't know, just t-test though too that you're taking a look at. Like you lose some power, but again, with these designs, it's generally okay because you usually have plenty of power to go through and test the things that you want to test. So again, it's just think about this trade-off, okay? And then think about Bonferroni density if you want to manage family-wise error. If this is you're noticing you have sort of maybe a number of different tests that you're wanting to run that are all a priori. These are both a priori controls, but if you're doing that, you may choose to do that, but by convention, you're not required to. Questions about sort of application of these or why contrasts are desirable to give you a little bit of a benefit. Okay. Again, kind of tease this a little bit, some things to be thinking about. Our traditional approach to calculating contrast, pairwise comparisons involves pulling that error term from my overall repeated measure ANOVA, okay? And provide more powerful tests, and this is a very, very good thing. But what we know is when we do this, our results can be sensitive to violations of homogeneity. There's the sphericity issue, discrepancies in cell size if we have a sort of between factors thing going on. As my designs start to get more and more complex. So just as a heads up, like we can have repeated measures analysis where we have multiple within group factors, right? Which is then sort of like we've got like parallel trajectories running. Like these designs get very, very complicated. As they start to get more and more complicated, there's more and more assumptions and more stuff can go wrong. Okay. So again, and this is just based on recommendation from Hal. It's such a good text and saying like, yes, here are all the things that you can do, right? And in our history, particularly sort of within sort of experimental area, there's a lot of like, as people were working through these methods back, oh, there's this way you can do this way you can do this, and like these really, really elaborate, like complex types of designs that you get, which are awesome, and they're all predicated on some very specific types of assumptions. And we know that applied data analysis is dirty, and we're generally making the best of the worst solution that we are with a bad solution, trying to choose the least bad option. Sometimes just falling back on paired sample t-tests. It's easier. It's easier to explain. Oftentimes it doesn't make a difference in terms of the power we've got. So sort of wanting to recognize if there are reasons to go through and we can utilize these contrasts, that's really nice. And it can make sort of things more efficient, but also recognizing if we're in a situation where, yeah, it starts to become really questionable whether or not we can start pulling stuff from my overall Anova to drop in there. I've got violations of homogeneity of variance very clearly. I've got problems with unequal samples in my between. I'm just going to sort of simplify. That's a completely fine thing to do. Okay. So again, it's doing this well involves a holistic approach to thinking about like, how am I going to go through and approach this? For our problem set, I'm going to just tell you how I want you to do it, right? Like you don't have to think about it. I mean, like I'm going to tell you, and then you're going to have to figure out like, okay, based on my hypotheses and what I'm saying, how do you go through and lay that out? But again, when you get into your own work, I want to think very carefully about, okay, so there's like sort of joke about sort of dogs, sort of like, oh, I caught the car. What do I do with it now? That's oftentimes what happens with this. Like, oh, I have this big design, went through and got my stuff. Now, how do I go through and sort of tease this all apart? Okay. Questions up to this point? Okay. All possible comparisons in SPSS, you can get this pretty easy. You just go to options in your repeated measure window, check compare main effects, and then you just correct whatever procedure that you want. LSD, Bonferroni, Dunsidic, none of these are sort of Bonferroni and like here's the thing. Bonferroni and Dunsidic, are those post hoc comparisons? Nope. Shouldn't do that. LSD, would you remember what LSD is doing? What's the correction in Fisher's least significant difference? There isn't one, right? So this is just running contrasts on sort of individual sort of pairwise stuff. Basically, what if you select what LSD is doing? LSD is just going to generate for you pairwise contrast using the formula we just showed individually for all possible pairwise components in your repeated measures without any correction. So you can actually shortcut that if that's what you actually want, and you just want, if you actually want to get and are comfortable running just a pairwise contrast, you can have SPSS do it for you. This is how you get it, right? But you have to know how to get it, what it's doing. This is just running that without any sort of correction, right? So again, even the options that SPSS provides you is like an inappropriate use of these versus no correction on this, right? So it's not doing you any favors unless you're hacking it and saying like, oh, what I really want is a comparison using that within groups contrast of time one at the first and the last time point. I can run that by hand, or I can just have SPSS throw this out for me, and I just know which one to go through and interpret because it's going to give you the same thing. Okay. So, well, no correction for sort of LSD. That's just your paired sample contrast there. Bonferroni and Dunsidic aren't post hoc tests. And again, it just ends up being, and I'm again not passing judgment because I've done it too. Like I just want to see what I've got. So you drop it down. It's really easy to go through, but then we have to be careful about recognizing what we're doing and sort of how we've gone through and approach it, not trying to pretend that I had some idea about something before I actually sort of even started looking at p-values. Other thing we can do is we talked about this last semester. We can bend Tukey to our will, right? Everybody loves Tukey, probably just because it's fun to say Tukey, right? But remember that Tukey correction works off a slightly different table Q, right? And Q critical, we have tabled sort of critical values for that. And those critical values are based on alpha, the number of differences between means, and the degrees of freedom error that you would get from this. Sort of the thing to remember is T critical has a direct relation with Q critical. It's just T critical is equal to Q critical divided by the square root of 2. What I can do is go through and generate sort of a number of tests that I want to correct for, go through, identify Q critical for that, and then just go through and run some t-tests and test them against my Q critical that I turned into a T critical, and then sort of run through and do some stuff, right? So the issue is, remember that Tukey will give you all possible comparisons sort of between a series of groups. And so if I have, and so the formula for that is n times n minus 1 over 2, right? So if I have 1, 2, 3 means, and I want to look at pairwise comparison across all of those, I've got 1 versus 2, 2 versus 3, 1 versus 3. I have 3 possible comparisons that I can make for that, right? Or I can just say 3 times 2 divided by 2 is 3. That's sort of getting these here, right? So if I had, say, 5, that's 5 times 4 divided by 2, right, is 10, right? So if I have 5 means, there's 10 possible pairwise comparisons. That's essentially what Tukey is doing, right? Tukey is controlling for all possible comparisons. So then what I would do is, if I have, like, say I've got 5 means, so R is going to be equal to 5, alpha is 0.05, and then degrees of freedom error is whatever that is from my overall ANOVA table. Let's say it's 50 or something like that. I would just look at a Q critical for R equal 5, alpha equals 0.05, and with 50 degrees of freedom, and it'll give me a Q critical. And then what I can do is take that Q critical, turn it into a T critical, and then just start running all my t-tests and then compare them against that and say, this is controlling at 2-key alpha less than or equal to 0.05. You're not getting, with a traditional 2, you're not getting specific p-values for this, right? Although you can now, right? And so what you could do then with this is, let's say that I have a set of 4 means that I want to compare against, right? The question then becomes, what do I set R to, right? If I set R to 3, I'm controlling for 3, and that's not 4. If I set R to 4, I get 4 times 3 is 12 divided by 3, 12 divided by 2 is 6. 6 is too much. So then, like, so I can't get an R that corrects for 4 exactly. But I can say, like, well, maybe I'll go set R equal to 3. Even that's 1 less test, but maybe I go through and I'll set alpha to 0.01. And then across these, like, you can start to kind of like futz around with stuff and get something that's kind of close. In the publication of my dissertation, like, I did this because it's the best procedure I had to know how. But again, it's just it's kind of a little bit of horseshoes, right? So this is something you can do. Howell has talked about this, but so the issue is, right now, probably have a better, I'm presenting it because it is a thing that you can do. Right now, what might be the better approach to take if you're sort of having sort of a set of pairwise comparisons that you want to compare that doesn't fall exactly in something that you would get with Tukey. If you think Tukey is fun to say, Benjamin Oxford is even funner to say. Okay, what we're doing here, remember, this is just a slightly different approach, and one that I like a whole lot. Okay, it's a little bit different. With our conventional or traditional post hoc approaches, What we're doing is we're concerned with managing family-wise error, right? And so the underlying assumption with family-wise error is if I make even one error, the whole set is blown, right? If I make even one mistake, if I even say that one effect is there when in fact it is not, then the whole set is ruined, right? Benjamin Hochberg is using a false discovery rate approach, which is a little bit different. And what this is going to do is say what percentage of my significant effects are false positives, right? And what we're going to try and do is manage that. And what's really, really nice is we get with a Benjamin Hochberg an adaptive p-value that goes through, and as I'm starting to test means that are farther and farther and farther apart, Charlotte, what happens to my p-value that I have to do to sort of claim victory on those?
So sorry, could you repeat that?
Yeah, with Benjamin Hochberg, is my sort of means that I'm comparing and get farther and farther and farther apart. What happens to the p-value that sort of is needed to claim victory on those?
Smaller.
You get smaller, right? And so the idea is, Catherine, you cannot just look at your data set and say, ooh, I want to see if these two things are different, right? Because they're the farthest apart. You can, but with Benjamin Hochberg, what you're going to do is you're testing all the other stuff. And so this might be like the 6 or 7 actual in terms of distance that you're getting, right? And you're going to get taxed for that more than the stuff that's closer together, right? And what this is this is really slick. It's not dependent on identifying a value of R that actually gets at. I can have 13 comparisons if I want to. There's no R that gets you to 13, right? And so it's a nice way to go through and approach things. It gives you a little bit more of an adaptive criteria. So what we're going to do for our Benjamin Hochberg procedure is we're going to determine a critical p-value for successive contrasts as equal to I over K times alpha. I is your test index. This is determined by just ordering your tests up from the smallest p-value to the largest p-value, or the largest p-value to the smallest p-value, and then K is just the number of tests that you have. So here, if I were to take into account, so I've got 4 groups, right? If I didn't want to use Tukey, what I could do is I could go through and run just my t-tests for all possible comparisons. And this is for my our inpatient BDI, our ordered means. Okay. What I did is we've got 4 assessment points. So I've got 1 versus 2, 1 versus 3, 1 versus 4, 2 versus 3, 2 versus 4, 3 versus 4. That's all possible comparisons that could be made within this set of ordered means. What I do is I just run the paired sample t-test for each one of those time points, order those from my smallest t-value to my largest t-value, okay? And then my index is just going to be the number of tests sort of down 1, 6, 5, 4, 3, 2, 1. And then what I'm doing here is I'm just going to go through, and for each one of these tests is going to have a different p-value, right? So here my index is 6, number of tests is 6, 6 divided by 6 is 1 times 0.05. That gives me 0.05, right? But here's where we're going down, we're seeing my p-value get more and more stringent, right? So the stronger and stronger signal I'm getting, the more tax that I'm applying to this. This is a really, really nice post-hoc procedure that can be used flexibly. If you really do want to look at all possible comparisons, just use Tukey, that's easy enough, right? But if you're looking at what I'm wanting to do is an exploratory fashion, so look at these specific ones. This is going to end up with 8 specific contrasts. I can just line this up here and sort of go through and manage those in sort of an exploratory fashion without having to try and finagle Tukey. And so you can do this, but you kind of get into a horseshoe situation here. This is just a much cleaner way to go through and do it. Okay. You remember, so Benjamin Hochberg, as you were going through with this. Okay, cool. Let's go through a break there. Let's take 10, come back and we'll talk about sort of considerations on effect size with some of these. Sound good? Katie and William, thank Jack and Charlotte for reminding me to reach out to this. So telegraphing the comments to them. All right, so, want to think about effect sizes, how we go through and get these for, our, within groups contrasts for our one-way designs. Like anything else, we need to be thinking about what we're using as our standardizer. Remember that any D statistic, is going to be interpreted as sort of standard deviation different, or standard deviation difference across means. We want to be thinking about like, what do we use as an appropriate standardizer for this? And please note that this down here in the bottom, D equals psi over S error. That's not your standard error. Don't do that. If I were to divide psi by a standard error, what does that give me? Is that an effect size? What if I take a mean difference and divide it by a standard error? What does that give me? It's a T statistic. It's not an effect size, right? So be careful and think about like what you know about effect size and what makes sense. This is just a standard deviation of some error term here is what we're doing here, okay? And it starts to get tricky when we're thinking about these repeated measures designs, okay? Because there's a lot of different things we can go through and do. For certain, if we're going through and we've got a situation, again, Charlotte, go back to the example that we were talking about with you. Let's say we're have a multiple baseline type of design. How advocates in these situations going through and using the standard deviation of participants' baseline scores, okay? So let's say we've got here a situation where we've got baseline, some intermediate thing, and then sort of endpoint here, right? And so let's say that the contrast that we want to run is looking at the combination of time points A and B relative to D, right? So we could go through, we talked about how to go through and create a contrast for that, we could set that up. But then the question is, how do I go through and create an effect size for this? So psi is easy, that's just the value of the difference between, so we have this is going to be 3, or 8 minus 3, 5, that's easy to do, right? But what do we use as our standardizer here, right? I could use variability at time 1, variability at time 2. I could use variability, but like it starts to get tricky because I've got multiple points here, right? One thing that Hal talks about is for situations like this, what maybe I'm going to do is go through and look at the combination. So for person 1, my value at the mean of assessment point 1 and 2 is 3. For person 2, the mean is 11. For person 3, it's 25.5. The mean for the fourth person is 30.5. You see where we're getting at? We're just looking at the average across these. And then what Hal says, maybe so then what we could do is independently look at the standard deviation of those mean values. And this is going to give me my standard deviation for my baseline. And then I take 5 divided by so whatever that value is. Okay. What we're talking about here is a very, very bespoke way of going through and assessing magnitude of effect. But this is an option that would make sense if you're wanting to go through what is Hal basically proposing here. Jack, if we're thinking back to some of our effect sizes for last semester, if we're looking at using the standard deviation of baseline for a standardizer, what do we?
It's like where you have like an original like to contrast to. It's like the G, or I forget the letter.
Not quite G, but you're on the right track, yeah.
Is delta?
Delta, right? We've got sort of a baseline. We've got a true baseline. We've got a true standing point. Here, we do have a true baseline. This is just let's say this is just like people existing in the universe, except we've added a wrinkle because we've now got 2 assessment points for that, right? What Hal is advocating in this specific case is literally going through and basically sort of generating a version of Glass's delta. It's just the standard deviation at baseline is the standard deviation of the midpoint of these for each individual person. Which is really cool and meaningful, right? Because, again, we should probably see similar variability here and variability here. Are these standard deviations gonna be identical? No, they're sure not, right? And if I choose one, it's gonna result in a bigger estimate than the other, because one's gonna be smaller than the other one if they're not identical, right? What we're doing is we're just sort of alleviating me of the burden of having to choose which one of these is the better baseline measure by just taking the average of scores across these and then creating a standard deviation based on the average of those. And now we've gone through and got a solution, okay? So again, just a lot of thought that needs to go into thinking about, like, what am I gonna do? What's best representative of the type of effect I'm looking at for here? Classic paper by sort of these folks. Never clear on sort of how that works, but you'll see this paper a lot. This is like a sort of a foundational effect size paper. Looking at the pooled standard deviations of the cells included in the contrast, right? And here we're just setting up pooled standard deviation, right? And we're going through, remember pooled formula for pooled standard or pooled variance. Always working from variance estimates. We've got n-1 times variance of 1 plus n-1 times the variance of 2, so on and so forth, divided by n minus sort of whatever number of terms those we have in that situation there, right? This can be a useful way to go through and just saying, I'm going to take the variability at time, the pooled variability at time A, time B, and time D, and just go through and take a look at that, right? Now, if this is set up where these are two baselines and that's an outcome, do I like this as a solution? No, I like Howell's as better solution, right? Because I have a nice sort of like, this is just the original state of affairs, right? But this is vignette 1, vignette 2, vignette 4. There's no true sort of thing that should, so this is maybe a good option, okay? But remember, when you're going back through and revisiting notes from last fall and sort of calculation of pooled variability, remember that we're always first working with variance estimates. And then once we got that pooled variance, then take the standard deviation of that. You get a different number if you're using that to get pooled standard deviation. That's not the correct estimate there. So just be careful of that. Okay. Also, in our one-way designs, do we actually really need to pool anything? Why not, Finn?
Because it doesn't really, I don't know. I don't know how to explain that. We just go.
Yeah. Why, anybody help Finn out? We can, certainly. Does it hurt anything? No. Make things more complicated? Yeah, why does it make things more complicated? What do you think, Catherine? What is the benefit of pooling, right? When we say like, oh, pooling is really sort of something we need to be concerned with.
If you have an unbalanced.
Yeah, it's different effects, right? Because the thing is that we know is the estimate that if I'm, let's say, I'm looking at a independent sample t-test, right? And I've got 10 people in this group and 50 people in this group. The assumption of equal variances is that sort of population variability is equal across those two, right? So D just says difference in those means divided by standard deviation. You say, well, doesn't matter, you choose which one you want, except one's gonna be smaller than the other. You choose the smaller one, it's gonna make your effect size bigger, right? Well, you make, oh, just take the average. Well, one of those has more people in it and is probably a better representation of the population variability than the other. We don't want to ignore one, so what we're going to do is we're going to pool, right? So we've got a weighted value for each one of those, and what's going to carry the most weight, assuming that our homogeneity of variance assumption is accurate, that variability is the same across populations. We're just giving more weight to the more precise estimate, right? But here in our one-way design, do we really need to worry about pooling? No, because it's the same people, it's the same number across all of them. So you just shortcut this, take the average of the variance of what you've got. So take the square root of that and it'll get you there fast, right? Just recognize that you can only do that if you've got identical numbers of people. Otherwise, you're just looking back. So. Other thing you can do as an option, pooled standard deviation of all the cells in the design. When might we want to do this, right? I would say in this situation, if I do not have concerns of violation of homogeneity of variance, right? More data I have, the more stable my estimate becomes. And so if I just have no concerns about the variability at point A, B, C, and D, it's all about the same. Maybe I'll just take the pooled variance of all time points and use that as my standardizer. And then that's fine too, right? So again, just kind of depends on how you want to go through and set things up. Or if you just have sort of, this is sort of if we're sort of running a true contrast, if it's just to a pairwise comparison, then we're just back on sort of considerations we had in the fall for effect sizes for paired sample tests between sample tests and things along those lines. Just take note of this. This is still a little bit of a Wild West show, right? So like, I mean, having confidence bounds on a repeated measures effects. SPS provides these. I'm not sure exactly how they're calculating those and what sort of the statistical or methodological process is. It used to be easier to get under the hood, see in technical appendices what that is. I don't have been able to find that right now. This tricky thing is that because confidence bounds around effect size is based on a non-centrality parameter, that non-centrality parameter is pulled from our test statistic, and our test statistic is using a very specific value of error in calculating that. If you go through and standardize your point estimate with a different value that you use your test statistic, what you'll get is an effects or a confidence bound that doesn't actually include what you'll often get is confidence bound that doesn't include your point estimate, which is very clearly not an okay thing, right? And so there's some stuff that sort of kind of goes on with this. Generally for effect sizes, what you should be using then if you want to calculate a confidence bound around that is this standard deviation of your difference, right? Because that's what you're getting. That's what goes in the calculation of your paired sample T. Remember, it's first observation, second observation, and then the actual stuff that's going into the calculation of your t-test is the difference, the standard deviation of the difference. Problem with using standard deviation, what's the problem with using standard deviation of the difference score in terms of using that as your standardizer? That can be really huge, right? If we look at standard deviation of the difference scores across these two time points, it's 2, here it's 7 and 1, right? The actual variability by difference scores here is going to be pretty tiny. If I look at standard deviation at time 1 and standard deviation at time 2, it's really big. If I use standard deviation of the difference scores for my paired sample tests, what can happen is I can really inflate effect sizes beyond what is reasonable to interpret based on what we're seeing. So we got to be careful about that. Okay. The other thing too is you will see in the calculation of effect sizes, measures that go through and account for the correlation between assessment points as kind of a correction. These are nice because they will give you very, very large effect sizes. And these types of analyses are important for calculating power, but they're really not great for calculating like an interpretable effect size because one, there's a correction for the correlation in there. So I can't just talk about this as the standard deviation unit. That is the difference in standard deviation units because that I've rescaled things, right? The other thing too is that effect size is nice, but it's also wildly inflated and be like way bigger and overrepresent the actual difference that you did find. So you got to be careful with those. Anytime you're going through and reading a paper and someone's reporting effect sizes, make sure that you know how they're calculating those effect sizes, and if they haven't told you and you're reviewing that paper, make sure to say, hey, you gotta tell me how you calculated this, particularly for repeated measures, because otherwise I can't really interpret what's happened, so. Okay, so what we need to do is we need to go through for our two tests. So remember, I guess, so questions about effect sizes. So this is really hard, right? I wish I could say, here's the right way to calculate effect sizes for these designs. I can't, because there's lots of different ways. It's going to depend on what you want, how you want to interpret things, and what your design is, and what your question is. And it's probably might differ from sort of comparison to comparison, right? So it just takes a lot of sort of background know-how. Think about like, what am I going to do? What makes sense? So my standard for, is it a good way to go through and do things? Could I stand in front of colleagues I respect, so to say, here's what I did, and sort of feel comfortable with them, sort of judging my analytic choices and sort of my inferences from that. Okay. So, okay. Let's jump in to talk about how we might start to tackle our sort of follow-up tests for our within group designs here. Okay, our one-way tests. Remember that what we did with our first inpatient group. Cindy, do you remember what we did with our first inpatient group? What were we doing here, and what did we find for our ordered means? So we're looking at reductions in depression symptoms over the course of inpatient treatment at baseline 2 weeks, 4 weeks, and 6 weeks, right? And what did we find from that? What do we find in that omnibus test?
Yeah, there was like a general like downward trend, or like not downward trend, but like that we're seeing that scores were getting lower.
What's that?
The scores were getting lower.
Yes, scores were getting lower, right? If I go through. Yeah. So we were going through and getting on our repeated measures, we were seeing reductions over time, right? And so the question then is, how do we go through and sort of tease this apart? Okay. What are things that I should be thinking about in terms of how I'm going to go through and assess that? What are considerations? What do you think, Jack?
Looking at the difference between BDI at 6 weeks and BDI at baseline.
Yeah, right. If we're looking at this, we're seeing massive, and if we go back through and look here, I was at the handout for this, we're seeing massive drops over the course of treatment, right? And so wanting to think about like, what is the question I really want to ask? Now, is there a reason to ask whether or not reductions, if there are reductions from baseline to week 2, or week 2 to week 6, or week 2 and no. And if I just look at it, it's very clear that there's things are dropping, right? So even though, could I, in this design, if I've got 4 assessment points, right? 4 times 3 divided by 2, so there's 6 different possible pairwise comparisons that I could sort of pull out of there that would be unique. Are all of those interpretable? Yeah, I mean, this is just all within sort of one thing. I could say 2 is bigger than 3 is bigger than 4. I could go through and do that. Is that useful and for meaningful information that anybody's interested in? Probably not, right? So what I could do here is just default into a paired sample test. And even this is gratuitous. Is baseline different than outcome? Obviously it's going to be. But if I want to go through and look at sort of just to run this to talk about magnitude of difference, what I could do is just very simply just default to a paired sample test, right? And so yes, my overall repeated measures ANOVA is saying I'm seeing differences in pattern of means over the course of assessment points. We don't have to overthink this. It's very clear what's happening to this, right? And so if I go through and just go through, and this would be not to get a p-value, because p-value is obviously going to be obvious, right? But I just want to get a effect size for the magnitude of reductions, and then maybe go through and think about like what it is if people for what is the average amount of change or average reduction that we're seeing in BDI scores, and for anybody else running this type of thing with this type of program, what's like so the range of data supported population changes that we might expect. I can see that as being a useful thing, right? And so that's essentially what we've done here, right? Just in SPSS, we're looking at the difference between 6 weeks in intake, right? We're going from a BDI score of 26 down to about 8.5. That's obviously a massive reduction, right? And so I can go through and I can run my paired sample t-test. I don't need like that's a t statistic of 27.6. That's math. Like I need to go through and report that because it's obvious, right? But what I will get here is effect sizes, confidence bounds around that, and then confidence bounds around what I'm seeing here, right? So if we were to go through and write this up and just break this down to a pre-post, we're saying follow-up analyses indicate an average reduction of 17.8 points on the BDI, population estimates ranging from 16.5 to 19. Okay, and this is on this most current the logistics set. So I'm wanting people to continue to sort of think about like some practically meaningful stuff. If I'm going through and I'm a clinician, and I'm saying anywhere from 60 to a 19-point reduction in BDI scores that I could expect from people doing this, I'm like, it's pretty good, right? I'm liking that. Even the low bound is a lot, right? Responses exceeded conventional benchmarks for large effects with patients demonstrating nearly a 1.6 standard deviation change in scores over the course of intervention, right? This is just sort of going through a lower bound estimate of the population effect in these data continued to support reductions in excess of 1.4 standard deviations. Here I'm just, yeah. Right, so we're just going down through, I've got 388 people. Do I need to worry about a hedges correction here? No, right? So again, even the low bound, the most conservative estimate of an effect size I'm getting for here is suggesting still almost a 1.5 standard deviation reduction in scores. That's sort of still impressive, right? Results offer substantial support for large clinically significant change, global progression for individuals receiving inpatient care, right? So see, we've gone through and taken this and sort of pulled this together in something that's clinically, practically, and statistically meaningful in describing what we're seeing within the context of this study. Okay, but as opposed to follow-up tests indicated significant reduction in depression. Like this is what you see like all the time. This is far, far better and more informative than wishing statistical significance, right? Nice snooze, right? I mean, like, yes, it's true, right? But you're just not using sort of everything that's available to you to go through and really talk about like what are we seeing in this phenomena, how to respond to it, things along these lines. Before we go through and do quick there we go. And looking at our output here, okay, just as a reminder of what that looked like, right? So again, this is what our data look like in terms of plotting this out, right? We've got massive reductions, right? These are all clearly different than one another, right? There's really no like reason to waste p-values and things. I mean, like, it's not even a waste of power because it's so massively different, right? But the question started to become, do I really need to look at all possible comparisons here, or can I just very easily say, hey, there are differences? Now, if someone wanted to say like, is there something critical going from week 1 to week 2? And so like for inpatient stuff, question is like, how long do we keep people in inpatient? Do we get them down, right? Like, I mean, there are questions to be had, but if those aren't the questions that you're asking, no reason to go through and spend a whole bunch of time going through and sort of pulling things out here, okay? And so that's where here we just drop down, run a t-test and are sort of okay with that. One thing I wanted to highlight in this is this table where we've got our within subjects contrasts. Okay, remember this is our linear our polynomial contrasts or our trend analysis. This is where this lives in SPSS. Okay, and if I go through and I take a look at so my test of my linear contrast, I've got an F of 730, not like it's wild, right? So it's suggesting that I do have sort of a pattern of means that is different than zero, consistent with a sort of linear sort of reduction here. I also see evidence for a quadratic, right? Jack, would we interpret a quadratic here? Could we interpret a quadratic here?
No.
Well, we're thinking about quadratic as being sort of a reduction in change, right? So like oftentimes it's sort of the other way. Don't here if we're sort of flipping this around. What we could do if we want to do is we could say, well, we're seeing some reduction that's tapering off over time, right? Which is generally not inconsistent with what we would expect for treatment effects, because there's probably not just like straight down linear change. Like at some point you're gonna kind of hit a floor and kind of follow out. Now, full on quadratic, you're right, would end up coming back up here. Do we think that we're gonna keep you long enough for things to come back up? Probably not, right? But what we're getting is this section of the polynomial that's capturing this curve right here. So I could make an argument for making an interpretation about the quadratic, and we are seeing that so the effect size associated with that is not nothing, right? I mean, so and probably if I were gonna model these data with like a growth curve model, I would include a quadratic term in there to account for the fact that things will sort of decelerate as we're kind of going through. Okay, but we also go through and we see you've got p equals 0.002 for a cubic. Okay, cubic is going down and then sort of coming back up and then back down. And these are giving us evidence for this. Does it make sense to interpret a cubic here? Oh, right. There's nothing in these data suggesting a switching in functions, right? We're not there. Like, I don't know what this is capturing, but it's not anything that's useful in these data, right? So again, knowing particularly in a sample of this size, if you're going to think about trend analysis, this will sort of just continue to go down. You get, and what will happen is like the fourth order polynomial will not be significant, but then the fifth order will. Like, good luck trying to explain sort of why you're actually seeing that type of thing. SPSS will just dump out whatever. Be very, very careful with this. Okay. Could we use a trend analysis to describe what we're seeing in this pattern of means here? Would that be a fair thing to do? Yeah, it would be a fair thing. It would be a way to go through and efficiently capture this. We're not trying to look at individually, so what's going on. We're just saying, in general, do we see reductions here? We do. They tend to sort of like, certainly we can model that as a linear function and probably a quadratic in terms of things following down. But also, if I was really interested in sort of that, I should just use a different model of this if that's what I'm talking about, right? So for us, just the pre-post will probably be fine. You kind of seeing where we're at with this? Okay. Switching over to You live, Cindy?
Trying to hold in the cough.
That only ever makes it worse, been there.
Cindy's faking and choking to get out of like the last part of it.
Still there.
There we go. 6 times the charm. All right. So I want to go through and sort of then revisit. So for this one-way design, pretty simple, straightforward, right? For our unordered, so we got some different things going on here, right? So we went through, remember, this is our vignettes. We got 8 different vignettes, and we went through and took a look, and we look at our main differences across our individual vignettes. Again, we're looking at ratings of so whether or not people are willing to provide friendship to individuals involved in sort of different trauma and non-trauma scenarios. When I'm looking at this, stuff looks pretty grim because that all looks very, very, very similar, right? But given the combination of the sample size and the repeated measures design, what we were seeing is very clear evidence that yes, we are seeing differences across these means, right? And that our null model of equal ratings of friendship across all of these vignettes is not plausible based on the data that we've collected, right? Suggesting that there are differences in means here somewhere, right? Now, the tricky thing is with this, because there is no natural order, right? And so this is the pattern that we're seeing given the way I've gone through and entered these. I could completely scramble these up and it's going to be a completely different pattern, right? So if we go back up though and take a look at our test of within subjects contrast, we've got a linear, quadratic, a cubic, all the way up to a 7th order polynomial, right? Again, we have 8 assessment points, n-1 or k-1 is going to give us the order of polynomials here. And I have very strong and convincing evidence of both the 6th and the 7th order polynomial. Is there any way to go through and interpret that? Does that mean anything at all? No, because if I were to go through and reorder how I've gone through and put this, all this changes. There's no natural order of these data. All of this is ignorable and not something you would ever look at, right? Despite having very strong and exciting effect sizes here, like this just not. And what this is capturing is kind of this bouncing around of these means across sort of different stuff, okay? So again, just a difference in terms of how we're going through and looking at things, okay? So the question then becomes, how do we go through and start to test these, okay? What I want to have here is some sort of thought or procedure for how I want to go through and make sense of what I've got here. Okay, so remember what I have is I'm interested in sort of how people's willingness to sort of maintain friendship with survivors of certain types of stressors, right? And the vignettes that I have, I went through and counterbalanced these. I have people who are experiencing or giving people vignettes for folks who have experienced both what we would sort of in our field talk about like sort of big T trauma stuff and sort of other stressful things that are like impactful hugely, but probably not sort of trauma stuff, right? So this is what I have to make sense of, right? And again, we've got 8 data points. 8 times 7 is 56. Divided by 2 is 28. Is that right?
So 56 divided by 2 is 28.
Yeah, 28. Thank you. You know, it's really what caught me on the struggle bus with basic internal make fun of this big statistics I can't do basically quiet. But we've got who wants to go through and interpret and sort of report out 56 or 28 pairwise comparisons across each individual? No, right? And it's ridiculous and we would never actually do that, right? So what we need to be thinking about is like, what's the strategy that we would go through and tease this apart, right? Now, if I'm going through and I'm looking at this, there's all sorts of different things that I can go through. Remember that we've got sort of our first four here are trauma and our last four are not, right? I could be like, oh, is this one different than this one from this one? But like, I'm just cherry picking. There's no reason to like, I can sort of credibly come up with stuff, right? But what I could do, and maybe if we're thinking about this from an a priori approach, thinking about like, do people respond differently to trauma versus non-trauma scenarios in terms of willingness to provide support? And probably what I would and did with these data is I sort of assumed that people would maybe be more likely to provide support or report willingness to provide support to people who are experiencing non-trauma versus trauma events, right? And so with that, what I might do is just dramatically simplify things. Is my working hypothesis is that individuals will be less willing to provide support to hypothetical survivors of trauma versus non-trauma, right? What I can do now is set up a contrast where I'm just going through and looking at differences in the combination of these four versus these four. Okay. And now all of a sudden I've taken 8 data points and reduced that down to a very simple contrast that's addressing the question I have. Do people respond differently to trauma versus non-trauma events? Okay. If I were going back to the ordered means, right, where we just did a pre-post, that's certainly a fine way to do that, but it really is kind of a waste of the design in that like we've gone through and we've for the inpatient stuff, we've got baseline 2 week, 4 week, 6 week. And then we just ignore everything in the middle and just look at the pre-post. If we're gonna do that, just do pre-post, make your life easier type of a thing. Here, what we're thinking about is like, no, I don't know, I can't come up with one traumatic event, one non-trauma event. We're just gonna come up with examples of some of these and see on average, do people tend to respond to one with higher ratings of willingness to provide for friendship than others, okay? And so what I can do here then is go through and I can set up a contrast to compare these, right? And so I've got 8 individual means, right? X1, 2, 3, 4, 5, 6, 7, 8. Okay. How many sets do I have? 2, right? And how many means in each set? 4, right? Makes it pretty easy, right? I've got 1/4, 1/4, 1/4, 1/4, right? And then what I'm going to do is I'm going to assign a negative to these, right? And which one of these, based on my hypotheses, do I assign the negative values to? What do you think, Ben?
The group of like traumatic events.
To assign the negative one. So I'm saying that, yeah, yes, you were right. Yes, I'm going to say, here's my negatives for these, right? Because I'm expecting less of a response to the trauma than the non-trauma. Okay. So I go through and I do this. And so this is what's going on right down here is I've got 0.25 times mean 1, mean 2, mean 3, mean 4, plus 0.25 times mean 4 or 5, 6, 7, 8. I go through, run this out. Value of my contrast is negative 0.256. So you got about a quarter of a difference of a point here. Okay. What I'm saying here is my effect is negative, right? And so, Jack, to your question previously about like where do we go through and assign these? If I've gone through and done this, if my hypothesis is consistent, I should see that my non-traumas are higher than that, but I've got negative here, it's not. If I look at my means, it looks like sort of I've actually got something in the opposite direction that I had anticipated, right? So what I'm going to do now is, okay, I got to value my contrast. The other thing too, if I take -1 or the absolute value of -1,4, -1,4, -1,4, -1,4, +1,4, +1,4, +1,4, +1,4, add those all together. What do I get, Catherine? 2. I've got a standard set. And so I can, because I've got a standard set, I can interpret the value of my contrast as explicitly the sort of like observed difference across the average of these means, right? Now, could I have set up a different system here? Yeah, absolutely, right? I could go, yeah, I go -4, -4, -4, -4, like, I mean, however I want to do this, right? If I wanted to, but it's gonna change the scaling. I'm gonna get something that's different. But 0.25 is easy to do in SPSS. Right here, I'm doing it all by hand. That would be a fine way to do things. But like literally, this is saying on this scale of what is it, 0 to 8 or 1 to 8, I'm seeing about a quarter of a point difference across trauma and non-trauma vignettes. Okay. So once I got the value of my contrast, what I can do then is then go through is plug this into my t-test formula. So I've got negative 0.256, the value of my contrast, times we got the square root of and this is just shorten this up, right? We've got 1/4 squared times 4, got those ones, plus 1/4 squared, or plus negative 1/4 squared times 4, which is giving all those, is just summing up the squared value of my weights, right? Multiplied by the mean squared error from my overall Anova table. Okay. Divided by number of people in my sample here. If I go through and I run this out, I get a test statistic of 6.244 with 1,177 degrees of freedom. That's huge, right? Basically, we're hitting Z proportions here. I basically run this on a Z test, right? Now, if I were to go through and look at this with a paired sample test, right? I would have degrees of freedom be equal to number of people in the sample -1, so 231 -1, which is still a very large degree of freedom, but nowhere in the vicinity of this, right? So my sort of threshold here is much lower. And so my p-value is 5.94 times 10 to the negative 10th. Here's S, here's base factor. And then to go through and calculate my effect size, what are my considerations in my effect size here? Do I have a good baseline to sort of compare against? No. I've included all assessment points or all vignette ratings in this comparison, so probably I ought to just go through and include all of these, right? Now, if I wanted to, and if I was, and that's what I did here, right? Because I'm using the mean squared error for my overall ANOVA as in the calculation of my test statistic. What is mean square code for in ANOVA language? Variance. It's just a variance. And if I wanted the aggregate variance across everybody, what could I do? I just take that and take the square root of that, right? And that would be something that could be used, right? But remember that sort of this term is only containing all the individual different stuff starts to get pulled out, right? So that's going to be a lot smaller. Got to be careful with doing that, right? So what I'm going to do here is I'm just going to take the pooled variance of all of my sort of observed things, right? And do I have to pool here? No, because it's sort of a one-way design. I've got the same amount. So I'm just taking the standard deviations that I pulled from up here and squaring all of them to make sure I got the variance, adding those up, dividing by the number of variances I've got, right? Which gives me a variance of 1.106. I take the square root of that, gives me an average standard deviation, 1.051. Take the value of my contrast, divided by that, and it gives me my effect size right here. And then if I want a confidence bound around that point estimate, so my best guess for the average difference in willingness to provide friendship across trauma and non-trauma vignettes is about 1/4 of a point, but recognizing there's going to be variability around that. What I can do is I can take the value of my contrast here, plus or minus my critical T for 1,177 degrees of freedom, drop that in there, multiplied by my standard error, which is what I already calculated here. I mean, I already have everything I need to go through and calculate my confidence bound. Just go run that out, and my confidence bound here runs from negative 0.336 to negative 1.176. That's just giving you my confidence bound for data supported differences that I should see across these two groups. Yeah, sure.
Sorry, could you just repeat what you said after the considerations for the effect size?
Yeah, just thinking about like, so what are my options here, right? Like, I mean, I guess I could use, and so the assumption, if I'm Cohen, right? The assumption is a homogeneity of variance, and so population variance across any of these should be identical. And so if that's the case, then it doesn't matter which one of these I choose. Not really, from a theoretical standpoint. From a practical standpoint, does it matter? Yeah, because like, well, some of these are gonna be bigger than others, right? If I'm going through, looking at my, I have standard deviations here, but they're gonna vary, right? And I want it to be representative, right? And here for this contrast, all 8 observations are being included. There's no real baseline to support like a glasses delta type of thing. And so probably my best bet is just to take average variances across these and just run with that.
Okay, gotcha, thank you.
Yeah. I mean, again, what we could do is someone give me, what is the square root of 0.776 or 0.766?
Wait, 776?
0.76, square root of 0.766.
0.875 and change.
0.875, okay. If I were to go through and I take one more calculation for me, Charlotte, if I take negative 0.256 and divide it by 0.875, what do I get?
Negative 0.292 or 293.
Negative 0.293.
Yeah.
Call it, okay. So, if I go through and I take a look, if I just go through and I use the mean squared error overall, just take the square root of that. And if this was a twin groups design, that would be fine. Like that estimate would be what I would get here essentially, right? But so the issue is if I go through and just snag that as my standardizer, I get a point estimate of about 0.3, 0.25. It's a difference because what's gone on with this, that's just from my means, that's my mean squared error from my within subjects table. That's got all my individual differences pulled out of there. So could you do that? Sure. Would I recommend it? Probably not, because I then can't talk about that as sort of a difference in standard deviation units because all the variability, individual different stuff is pulled out of there. And so it actually gives me a different estimate. Like this is nice and kind of like that. It's pretty small, but this is a better representation of what's actually going on with this. Questions about any of this? People kind of see how we took sort of a very complex problem and simplified it a great deal so that it just is more consistent with sort of a question that I'm actually interested in. Okay, a lot of this will be simplifying. Okay, there are lots and lots of things I could test here, but probably a lot of those aren't going to make a ton of sense. So as we're going through and talking about this, we're saying plain comparison, looking at willingness to maintain friendship with hypothetical individuals exposed to either trauma or non-trauma events, compelling support for incremental differences across event type, but in the opposite direction of what we hypothesized. Remember that, right? Like we had gone through, like, yeah, we found an evidence, but it's in the opposite direction of what we had expected. So this is an important thing to know, right? Always making sure we're identifying direction. Results found that participants indicated about a 0.256 reduction in willingness to maintain friendship when presented with vignettes involving individuals exposed to non-trauma versus trauma events. Lower bound estimate for the population differences indicated 0.18 unit reduction with upper end supported 0.34. Effect size for the point estimate discrepancy was small, suggesting about a quarter standard deviation reduction in willingness to maintain friendship. Okay. So again, talking about is this sort of reasonable? What does this might mean? Results provide strong evidence for incremental reductions in willingness to provide support in hypothetical survivors of non-trauma versus trauma events, although effect not predicted in the initial hypothesis, acknowledging this is opposite of what we had expected. Also not clear the extent to which such an effect may result in observable impact on behavior, right? And it's just like if the low bound is about 0.2 of a point on this, sure, but it might not make a huge impact, right? But this is where we come through. Just because small effects don't necessarily mean they're not meaningful, we'd say it's important to note that the methodological approach used in this study has a strong potential for social desirability responding, right? I'm just like the correct answer is like top of the max, right? Like if you like how much you willing to support, maintain, like the right answer is just the high end of it. And that's generally what people do, right? And so given the context of the design, if we were to use some more behavioral types of approaches, so we say this might very much underestimate differences that we're seeing in here, right? And so again, when we're thinking about strengths and limitations of our design, I always think about a yes and type of thing, right? Like, yes, it's small, and maybe here's some things that we might want to think about things. Because otherwise, I just went through and did this. I'm like, oh, well, I guess this isn't meaningful. Trash bin, right? Or overrepresenting what's back. Oh, there's a huge difference if anybody's actually sort of looking carefully, like, I don't know, man, that's like less than 0.2 of a point. Like, I'm not sure that that's really meaningful, right? So just thinking about like combining what we found with the design, kind of what we would expect, try and pull this into something that's sort of a comprehensive and meaningful discussion. And I will say you all have been good at sort of trying to pull these things together. So I'm sort of reminding you in your sets, but particularly for this last one, should always be thinking about like sort of putting things in context and thinking about like what might this mean about the area of interest. Questions about how we approach this? Okay. All right. So at the end of the day, from a relative standpoint, these one-way repeated measure designs are kind of simple. We're just saying like, if I measure something over and over again, do I see shifts around in means, right? Complexities, but the answer is pretty straightforward. But really not a lot of depth to this or things that are sort of terribly interesting with just a straight one-way design, okay? Where we start to see these designs get really exciting is when we layer in the between stuff, okay? And so what we're talking about here is leveling up into a mixed factorial repeated measures design, okay? And the way we go through and typically we'll report these as talking about an A by B by sort of however big the design is with the repeated measures on the final factor, those lines. Okay. And so if we go through and we take our one-way design, and then what we do is we add in a between groups factor in this, what we've got is a mixed factorial repeated measure or mixed factorial ANOVA design. Okay. And so in our sort of simple sort of extension here, I guess this isn't necessarily simple. What we've got in this design, we've got a 3x4 mixed factorial design with repeated measures on the final factor. Okay, we've got condition 1, we've got condition 2, and we've got condition 3. And what we're doing is we're measuring everybody at time 1, time 2, time 3, and time 4. So we got 3 different groups, all measured on 4 different occasions. This starts to get exciting, okay? And we're only going to work with two-way designs here. You can have multiple between factors. You can have multiple within factors. These designs can get very, very big. You just want to be really careful about it's easy for your eyes to get bigger than your stomach on this. And then all of a sudden we need a lot of people to go through and start filling in cells with stuff, okay? With this design here, okay, we've got both a between and a within. And if we think about partitioning this out, so same type of thing, it's just we're doing some different stuff with this. We got variability going in a couple of different places. Our sum of squares total is still our sum of squares total, right? It's the total variability across all of our scores. If I were to go through collapse all groups and look at variability across all individual scores, this would give it, and take the variance of that, this would give us our sum of squares total, okay? Computationally, this is just individual scores minus the sum of the square deviation of individual scores from the grand mean down here, right? So this is 150 minus 183, 78 squared, 44 minus this squared, 71 minus this squared, here, for each individual across each repeated method. The deviation from the grand mean, square that, sum that all up, it's giving you sum squares total, okay? And this is the total piece of the pie that we're working. Okay. What we then do, similar to our one-way design, is we split this off in a between and a within piece, okay? Our between is going to be sort of the difference in sort of the weights. This is the number of groups we have from the person mean minus the grand mean, right? So here we've got the person mean 81 minus grand mean squared plus this minus grand mean squared, this minus grand mean squared. So moving across there, we're just getting individual, the sort of mean group. This is just mean individual different stuff. We're pulling this all over off to this side. So again, just like before, we're taking our individual differences, we're pulling it over. It's just so we'll do more with this in a moment. Okay. And then we've got our of this down here. We've got our sum of squares group. Okay. This is going to be the number of people within each cells times the number of group, and taking the sum of the square deviations of the group mean minus the grand mean. Okay. That's right here. Minus this squared, this minus this squared, this minus this squared. We're getting overall variability across our groups. Okay. And this is going to give us our sum of squares group. And then whatever the difference is that's left over, that's our sum of squares of subjects within a group. That's just our error term here. Okay. Over here are sum of squares within. So this is getting sort of sectioned off whatever we've got left over, comes over to this point. Sum of squares repeated measure. This is our within stuff that we're getting here. And this is going to be the number of people times, oh no, W is the number of assessment points. So this is the number of groups, the mean of our repeated measure minus the grand mean. So we're going through and squaring that up, right? That's giving us this component. Sum of squares cells, this is a computational piece of things. You don't need to worry about that. But once we get, and our cells is basically our, conceptually what we've got going on is we've got our within here, and we've got our repeated measures, and then our repeated measures time our group, and then we've got our error term in here. Okay. So the thing to remember is sort of with this is what we're doing is we're taking the total variability in our data. And what we're first doing is pulling out all the between stuff. Okay. And then we've got our within. Okay. But we've got some different components within each one of these. In our one-way design, Catherine, when we pulled this off, our sum of squares between, what was that?
Or like the individual.
Yeah. What did that represent? Pull that between out. What was that?
Like individual difference.
I was just individual differences, right? And it's still that, but now what we've got is we've got a grouping factor, right? So yes, we pulled out individual differences, but part of that individual differences is we're seeing differences across group 1, group 2, and group 3, right? So what we can do is actually go through, basically what we're doing is we're pulling a one-way ANOVA model out of this whole thing. Okay. And then what we have left over is the within, and so we still have our repeated measure and we still have our error, but we've also got this group by repeated measures component. This gives me the interaction of both my within and my between. This is the sum of squares repeated measure times group. That's the interaction that we're most often interested in. Okay. So what I'm gonna get for these models, I'm gonna ask for my two-way design, right? I'm gonna get coefficients for three that are gonna address three different questions. Do scores differ across levels of factor A, collapsing across repeated assessments? Okay, so if I just collapse across my repeated assessments and I'm looking at just sort of where these scores are lying, so the average across these, okay? Am I seeing differences across groups? What component is that grabbing in sort of this whole sort of pattern here? What do you think, Finn?
Repeated measures.
Okay, so I'm collapsing across repeated measures. Repeated measures doesn't exist. I just have one score for person one in group one, person two in group two, person three in group one. And so this, what are we getting with this? If we're saying, if I collapse across repeated measures, am I seeing differences across group? Is that a grouping factor or within factor? So it's a grouping factor, right? Because I'm sort of asking about, like, does group A group different than group B, different than group C on the aggregate across assessment points? Okay. So I'm saying, regardless, I take an average across the repeated measures, am I seeing mean level differences in group one, group two, group three? Okay. And this is getting at sort of this piece down over here. I'm also going to ask, do scores vary across repeated assessment of factor B, collapsing across group? Collapse B is your repeated measure, okay? So if I ignore group, right? And I'm saying, do I see differences here, 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 and here? What effect is that capturing, Catherine? Yeah, the within. It's this piece right here. Saying ignoring group. Do I see differences across my repeated assessments? Okay, so my first question, factor A is my between. I've got a 3, and in this design, I got a 3x4 mixed factorial design. Here, okay. So first component is saying, do I see differences, mean group level differences here, here, and here? Okay, ignoring collapsing across repeated assessments is 137.67 different than 238.33, different from 175.33. Do I see overall differences across my groups collapsing across repeated assessments? My within is asking, do I see differences across my repeated measures collapsing across group? Do I see differences in 302.89 versus 158.78, 152, 121.44? If I ignore group, am I seeing sort of differences? Okay. And then the last thing I'm going to ask is, do repeated measure scores vary as a function of group? And where is this coming from? Jack, what component is that getting
I
at?
think that we over decide.
Yeah, so this is gonna be my interaction piece here, right? This new thing that we're adding, it does the pattern of means across repeated assessments, is that dependent on group, right? This is where we're gonna start to be looking at, for each one of my groups, what's the pattern of means that I'm seeing? Okay, and this is my interaction right here. And this is generally the thing that we're most interested in, okay? So again, then, show that we're talking about sort of looking at, so let's say, physiological responses across, let's say, 3 different vignettes in groups that involve folks who are neurodivergent who are not, right? What we've got is a 2x3, let's say 2x3 mixed factor design, right? And so the question is like, the question would be, do neurodivergent versus non-neurodivergent folks differ on overall level of physiological activity, collapsing across assessment points, right? It's just like you looking at that as sort of an aggregate thing. Are we seeing differences across these two groups, right? Then we can also ask is, do we see, ignoring neurodiversity status, are we seeing differences in physiological response overall across responses to whatever it is that you're showing them? And then what we can ask is, do we see different patterns of responding across neurodivergent, non-neurodivergent individuals, across these individual sort of conditions, stimuli, and things like that? And that's often sort of the thing that we're most interested in sort of looking at is, do we see different things across these different groups? And that's where these start to become really powerful, exciting designs. We just got to be careful with how we're using them. In your handouts, you've got a handout that just sort of a breakdown of sums of squares within these. Go through, take a look at that. You'll have in your final problem set needing to calculate generalized eta squared based on that Bakeman article. And you'll just want to be very, very clear where these different components are coming from within your output. Make sure that you go through, read through carefully. Make sure that you're understanding what these different components are and where they live in your output before you start trying to run things. Otherwise, it's going to be a mess. Okay. Questions about what we're getting with these mixed factorial designs? Okay. Okay, so look at that. We got some things. We got deviations of all scores from the grand mean, deviation of subject means from the grand mean, different deviation group means from the grand mean, deviations in the repeated measure means from the grand mean. Whoops. And then we've got, so what's left over with stuff. So here, yeah, we've got 4, W is 4, that's within, N is 3, the number of people within each group, and G is 3, the number of groups that we have there in terms of notation. All right. So for our mixed factors Anova, we've got a number of different assumptions. We've got some between stuff and we've got within stuff, and we need to attend to both. For our between subjects factors, we're assuming normality and homogeneity of variance across groups. These are no different. This is just like Anova stuff, right? I have asterisk normality. Why did I asterisk normality? What do you think, Charlotte? What does our normality assumption pertain to with our group level data?
A normal distribution across all folks, but
Okay. With our,
within the same people, so.
is it, are we with our group-based design, are we interested in sort of what we're actually seeing on the page, or are we interested in something else in terms of normality with group-based designs?
Difference.
What the difference, Jack?
Normality is assumed if the distribution of sample means.
Sample means, right? And again, it really, really important to remember this, because when we're doing our like regression, things along those lines, then we are like sort of the values on the page start to become important, right? Here, distribution of sample means that so long as we're pulling from something that's has a normal distribution in the population or reasonably large cell sizes, 30-ish, right? Our distribution of sample means will start to become normal very quickly, right? So even if we've got skewed, funky stuff in a group-based design, we don't need to freak out right away. It's something to note, certainly, but it's not necessarily a violation of our assumptions. Now, if we start to have people who are way far out, extreme values, we still need to go through and screen, be careful about it. But again, our normality assumption with our group-based design is not about the actual scores, it's about the distribution of samples. Right, starts to become important, because otherwise people start going through the wild ass corrections and transforms and things like that when you don't need to. It's not necessary. Okay, and then for our within condition or within factors, we want to again see distribution or normality in the distribution of sample means, say homogeneity of variance across intervals, and then that sphericity assumption. Right, sphericity is an assumption. Do we worry about sphericity a whole lot? Nope. Why not, Finn?
So we can't really achieve it?
Yeah, it's not a realistic thing, right? It's like my assumption is to be the smartest and most eloquent every time I step into a room, but that's not an achievable thing. So we just correct for it and realize it's never something we're going to hit. So we just kind of take it there, right? All right. So what we will do, and we will start with this next week, is we're going to go through and take these two data sets that we've already used and just expand. We're just gonna add a between factor component in there, right? And so what we have in our depression in our order means that we've had BDI samples at intake 2 weeks, 3 weeks, and 4 weeks. We already know what happens with that, right? But what we're gonna say is like, we've got different treatment programs, okay? Catherine, is your interest in sort of older individuals or psych? There's sort of serious mental illness psychos, more older individuals, okay? Let's say more, let's say you're other on the interest in the other area of Chris's stuff and saying, okay, we've got inpatient folks. And so to make, maybe these are people who are struggling with serious mental illness and things like that. We've got 3 different treatments, right? As people come into our center, we've got 3 different sort of like tracks that they can go through and follow. What we want to see is, do we see differences in trajectory of response across these 3 groups? So what we're going to get is we're going to ask, do depression scores vary over the course of 6-week inpatient hospitalization? And like, write this down. I know we're right at the end, but this is going to be really, really critical for understanding these designs. What, Catherine, what effect are we looking at with this question here? It's just the within. Ignoring what treatment group we sent people to. This effect is going to say, as we follow people across treatment, do we see differences in mean scores at each assessment point? Or at least one assessment point, right? The no model here is that mean baseline is equal to mean at week 2 is equal to mean at week 4 is equal to mean at week 6. Is this interested at all at treatment group? Nope, it's just saying collapsing across treatment group. Overall, are we seeing changes in scores over time? Okay. Then we're going to ask, do overall depression scores differ across treatment program? What's that getting at? Between, that's my group, right? And this can start to get tricky, right? This is saying, if I just take the average score from intake to 6 weeks, and I just take the average of that across individuals, do I see differences across treatment 1, 2, and 3? In this question, is that really an interesting, or in this problem, or in this design, is that really an interesting question? Not really, right? Because then taking the average of people's BDI scores at intake 2, 4, and 6 weeks, taking the average of that and just saying, do I see differences in those scores across my 3 programs? My model will tell me whether or not there's an effect there. I just don't know that that's something that I would be interested in looking at all, right? Just because who cares, right? It's a different thing. And like, I don't know what the average score, BDI score across your total inpatient to stay, what that means or how I would interpret that. So for this question, this is probably not a really, I mean, your output will give you an answer to that question. And it might be a very small p-value. I just don't know what you would do with that or sort of why anybody would care about it, right? So again, you're recognizing that depending on your design, you could get tests for things you don't care about, right? So I want to be careful of that. And then finally, does the pattern of depression scores vary based on treatment assignment? Okay, what are we asking here, Catherine? Bring us home.
Like the interaction.
Interaction. Do we see different patterns of means across repeated assessments for these different treatment groups, right? Or are they all basically following a parallel structure, right? That's what's getting, and this is a very, very, very sensitive test. You're able to, particularly with a sample of this size, you're going to be able to detect very, very slight deviations from the same across these, and maybe in situations where it might not, we might not know if it sort of means anything useful or not, right? Like, yeah, they're not exactly the same, but I don't know if there's any practical difference or anything we should be super excited about. I don't know if there's anything that's saying these are working different or that might have any clinical meaning or not, right? So again, pulling back that practical piece, just because I have a p-value that's small, doesn't necessarily mean I found anything that's useful or interesting to anybody, particularly within these designs because they're so powerful. Okay. So people seeing kind of where we're sort of getting with this order means what we're doing here. Okay, same thing down here. What we're doing is we're going to take our vignette study, and we're gonna add in a factor, okay? What we're gonna do is we're gonna shrink things down. We had 8 vignettes before. We're gonna like set those aside and just focus on our 4 trauma ones, right? So we've got a situation where we've got a friend who's been involved in a motor vehicle accident, combat deployment, sexual assault, natural disaster, and we're asking them, how willing are you to provide friendship for this person, right? But then we've got a between factor. What we're doing is we're saying, like, previously we already went through and looked at people's general beliefs about trauma, right? And this is just people's kind of orientation toward trauma and its impact. We've got a negative profile. People exposed to trauma are broken and crazy. Can't trust them. Stab you in the back, steal your kids, use substances, sort of all sorts of bad things, right? We've got a benevolent group, like trauma or fun. Okay, you know, sometimes it's not so great benevolent, like, oh, you know, they need to be on medication. Maybe, right? So they're sort of going through, but sort of generally more positive. And then some people who are generally positive, but like, unless it comes like, would you date somebody who's had exposure to trauma? Would you let them watch your kids, right? Like, are they sort of being good people to sort of work with? Like, you know, reliable, I don't know, right? So kind of an intermediate kind of group here, okay? And so what we're doing here is the question is, does willingness to befriend vary within person across different traumatic events? Jack, help me out. What are we asking? What effect are we looking at with this first question?
The first one is within.
That's my within, right? If I ignore belief profile, if I made sort of not taking that account, do I see differences in sort of willingness to provide friendship across motor vehicle accident, combat, sexual assault, natural disaster? Do I just see differences there? Okay. Does overall willingness to befriend differ based on belief profile? What effect is that? That's my between, right? It's saying if I average across responses across all of these, do I see overall differences in people in the negative profile, the benevolent profile, or the interpersonal profile? Jack, is that an interesting question within these data? Well, it sort of kind of depends, right? In terms of thinking about when we're talking about, are there differences overall and overall BDI score across the course of treatment? I don't know what average BDI score across 6 weeks of treatment really represents, or what I would do with that, right? Well, what about this? Here we're going through and we're giving people different vignettes in terms of saying, like, in general, how willing would you be willing to provide friendship across MBA, combat, sexual assault, and disaster? This might be something that we could actually interpret because the aggregate of that maybe starts to be just on average, how willing are people to provide friendship to survivors of trauma, right? And so here the design makes a difference in terms of what we're measuring. So in this, I could see this between as maybe being interesting and worth taking a look at. So based on that, so Jack, what might we expect in terms of thinking about where might we see sort of differences across those profiles?
That negative won't be willing to be friendly with people.
Yeah.
Traumatic events.
It's almost a manipulation check of like, did I get this right? Like, are these profiles, are these actually manifesting in the types of things that I would expect to see, right? And so what I might do here, I would ignore that between and not make any interpretation of it. Here, I might be very interested to see that, like, are these playing out the way that I would expect, right? Because if the negative and the benevolent are equal across this, then I'm like, if I actually, am I measuring what I think I'm measuring here, right? And so wanting to think about, again, that's why these designs are so tricky, is because something that could be completely useless and meaningless in one study can actually be kind of interesting and important in another one. So wanting to think carefully about what these are doing. All right, Jack, bring us home. So does belief profile impact pattern of friendship ratings across traumatic events? What are we getting at there?
Interaction.
That's the interaction, right? And what we might find is for, say, let's say our negative group, they're just like, nah, F them across the board, right? They're just like, and probably not, right? It's probably still like, yeah, mostly, but at least maybe so something that's lower doesn't matter across the board, right? And maybe the benevolent is like, yes, across the board high, like not really sure if we got actual intention or just maybe benevolent is just socially desirable people, right? But what we might find is that with the interpersonal, maybe it's like, oh, sure, for natural disaster and motor vehicle accidents, yeah. Boy, like, I don't know, sexual assault, combat, maybe. I don't know, right? So we've got a situation where we could see across these within this design, right, if we got 2, 3, 4, so the one, either my negative folks are just like all the way down here, right? And then my positive folks are all the way up here. And then my interpersonal group is maybe like sure, not so sure, sure, not so sure. Okay. Something along those lines. Now all of a sudden we've got a pattern that looks like this. We've got different things going on for that intermediate group, right? How many people, given the sort of the observed differences that we're seeing in these means, would you have to get in order to tease these out across each in a completely between design? The answer is a billion, right? Like it would just take so many people, right? But if people are serving as their own controls as we're going through and doing this, we've got an incredibly sensitive test to be able to tease things out. And the thing we want to make sure here, right, when we looked at that original like sort of spiky thing, those are huge, massive differences, and they're not. It's sort of a tenth of a point difference across things, right? So we want to make sure that we're taking into account scale. But again, with these designs, sort of doing some really interesting things and be able to tease out both within and between and the interaction of those in terms of what that looks at in terms of patterns and means. How are we feeling about this? Okay. What we will do for our last class is we will go through and spend time working through these as examples, okay? We'll walk through these last ones using our handouts, right? So to go through, take a look at those and sort of see if those are making sense. I'll also post videos, so if you want to go through and kind of walk through the SPSS things before class next week, certainly you can do that. You don't have to if you don't want to, but it'll just be me like with all these videos talking through like sort of considerations and things along those lines. You got a lot of time. I posted this. This isn't going to be due until the last day of finals. Okay. So you got lots of time, pair up with one another to go through and work on these, talk with one another, talk with me, right? What you don't want to do is just pick a strategy and like forge ahead because if it's not right, like, so like talk with me first if you're not sure before we move forward. Just a lot of decisions to be to make in this, but yeah, you got a lot of time and sort of the time and effort we put on the front end, giving us a lot of space here on the back end. You should be able to go through and work with stuff. So I'm gonna pick at it slowly, yeah, you'll be in good shape. All right. Yeah.
For this one, do you want us to do the same thing as last semester where we just hand in one, like?
Yeah. It's just one problem set. So whoever you and your partner, just tell me who your partner is. And so we'll go through and so there'll be three assignments, which is nice for me. So, all right. Feeling good? All right. Nice work, folks.
Thank you.